The next speaker is Valerio Bozza, and he will be discussing microlensing computations with VBBinaryLensing.
Okay, thank you. Can you see my slide?
We can't see it right now, no.
You can see it, yeah. Okay, so I will speak about VBBinaryLensing. So VBBinaryLensing is a microlensing compute. Sorry?
We can't see your slide right now. No, we cannot.
Actually, let me try once more. So, as usual, it works before and now.
We can see your screen now, yes.
Okay, that's good. Okay, so I will speak about the VBBinaryLensing, which is this microlensing computation code, which was also mentioned by Radek. And actually, we often discuss about problems and in computation. And so I'm very happy that he's also using and testing and heavily testing my code within his Mulens model, which is a widely used platform for microlensing modeling. So, very brief introduction about microlensing. So you know that microlensing occurs when the light of a background source is deflected by a lens. A lens might be a dark, any kind of object with a gravitational field. So it might be a star, a planet, a black hole, whatever. So if you had a very high resolution telescope, you could see the images being distorted and additional images being created by microlensing. But actually, since we do not have enough resolution, we only see an amplification of the flux of the background source. And this is what we actually see. Actually, there is a number of cases in which we have enough astrometric precision to see the movement of the centroid of the images, which is an additional constraint to the microlensing event, which is becoming more and more important and will be important with the Roman Space Telescope too. So, science with microlensing. Microlensing is very useful to understand dark objects, starting with planets. So more than 150 planets have been discovered by microlensing so far in a variety of configurations. More recently, also an isolated black hole for the first time was discovered by microlensing using the astrometric signal. So this was something new, because usually we only see black holes with an electromagnetic counterpart, but in this case we could only see its gravitational effect. Finally, we can also see free-floating planets with microlensing. If you have a very short event with a finite source effect, then it's likely due to a very small object like a free-floating planet. And there are a number of cases also in the Radek has contributed a lot to this topic. In general, with microlensing, you can have precision mass measurements of isolated and binary objects. So it's becoming more and more interesting also for study of stellar populations and planetary population, as it will be with Roma. Now the problem is the computation in microlensing, because in principle, what you have to do is to compute the images that have been generated by a lens. So this is a case of a binary lens, and you can see that as there are regions in which the source, when the source crosses these regions, which are called caustics, you have the sudden generation of additional images that disappear when the source moves out of these caustics. So this means that once you have additional images in the light curve, you will typically see additional peaks. And so in order to have a microlensing computation, what you have to do is to, sorry, it seems stuck. Can you still hear me?
Yep,
yes,
it looked like it.
Okay, yeah, so the presentation was stuck. Can you still see the slides?
Yes.
Okay, so it was just
computation
stuck.
and microlensing right now.
Okay, good. So it was just stuck for the few seconds. Okay, so in order to do microlensing computation, you need to reconstruct the images, and you have to do it at a high level of accuracy to get a good photometry and astrometry computation. And here we come with the VBBinaryLensing. So this is a microlensing computation tool, which is very robust and fast. It is built by the contour integration method. I will spend a slide about it. It's a public code, so you can find it on GitHub. It's written in C++, so it's very fast, but it's also importable in Python. And now the VBBinaryLensing library is also called by most modeling platforms, such as MuLens Model, as Radek showed, but also other platforms such as PyLima or Mulan, which are public. And this code is also adopted as a base computation code in the future Roman microlensing pipeline that we are going to build. So just a few technical details. We want to reconstruct the images generated by gravitational lensing. We do it by inverting the lens equation, and so we sample the boundary of the source, and we get the boundaries of the images. Once we have the boundary of the images, then we compute the area of the images by Green's theorem. But of course, if you want to be more accurate, you can also include parabolic correction, and this is done in the code. And we have a full error control. So this means that we have error estimators for each piece of the images. And so this can also be used to drive the sampling. So the sampling is not uniform, but is optimized so that it's increased where the error is largest. And finally, we can get limb ducting by repeating the calculation on concentric annuli. Of course, the calculation of the images can be very heavy, but we want to do it when it's really necessary. So if we are very far from caustics, actually the point source approximation works very, very well. And so in order to decide whether to go from point source to finite source, we have implemented a quadrupole test. So we start with the point source, and then if the quadrupole test fails, then we go to the finite source, full finite source effect. For single lenses, actually, as Radek told, it's possible to do everything analytically. But if you have the finite source effect, actually, this is done by the use of elliptic integrals. And elliptic integrals can be quite slow for the direct computation. So in this case, we prefer to use pre-calculated tables so that the computation goes very, very fast, keeping the accuracy. So this is just an example of use of VBBinaryLensing. So in this case, this is a piece of C++ code, and you can see that we have some parameters: the separation of the two masses, the mass ratio, the source position, and the source radius. Then we also have the linear limb darkening coefficient here. We set our accuracy goal, and so that's the call to the function. So the binary mag function is called this way, and so we can get the magnification and also the centroid position if we are interested in astrometry. So after all, it's quite easy to use even with a direct call. But there are also a lot of functions that can be used if you want a full light curve, not just one pointer, but a full light curve of microlensing. You can use this binary light curve function. So you specify your parameters, and then you get the light curve with this. You can also include some higher order effects, for example, parallax or orbital motion in the circular version or in the full capillary version. And finally, if you also have an event in which the source is actually moving around a hidden companion, then you have the Xalarep effect. So there is another set of parameters, and this has also been implemented recently with my student Paolo Rota. Now, what's next with the VBBinaryLensing? VBBinaryLensing deals with the single lenses and binary lenses. Now, the challenge is to go to triple or multiple lenses. But of course, once you have more and more lenses, you find issues with the numerical instabilities. So we have several versions of code that are actually working, but we still want to test them and find the best way to keep all numerical instabilities under control, to have the most possible robust code. So, and that's coming to conclusions. So VBBinaryLensing now is more or less the reference code for microlensing with a wide range of possible uses. It's it's included in our microlensing modeling platform. So basically, this is a code for computation. And then you have a lot of platforms with user-friendly interfaces, such as MuLens model, for example, that call VBBinaryLensing for the computation. And as I said, multiple lenses are on the way. And we look forward to Roman Space Telescope because it will be an incredible advance for our knowledge of our galaxy in many respects, from brown planets, free-floating planets, but also black holes and remnants. Okay, so that's all.
Excellent. Thank you so much, Valerio. That was wonderful. We have time for some questions. Does anyone have any questions? Feel free to raise your hand. Or if you'd rather, you can also pop it in the Discuss Talks channel. I do have just a small question, as long as no one else. Okay. So I was wondering, so for the pre-calculated tables that you used, how much faster did it actually end up making your code run, if you have any idea? What order are we talking about here?
I think something like order 10 or 100, something like that. So calculating elliptic integrals requires a quite long piece of code. Well, if you have a pre-calculated table, you just load it at the beginning of the calculation, and then you just have to find the correct position in the array and pick up the value. So it's much faster. So this is definitely much faster. Of course, you have to be careful, because if you want to keep the accuracy, you have to pre-calculate your table with a very dense sampling, and this means that you need some memory. So this means that once you load your table, this occupies some memory, but there is a good balance. So definitely, this is the best choice, I think.
Excellent. You actually answered my follow-up question about calculating those tables. Wonderful.